So if you did get a general idea about the function, now we can enjoy the second part. We are going to talk about image filtering. Okay, I think image smoothing and edge detection, just two of the example of the image filtering. Okay, but I think we are going to take these two examples to give you the general idea about the filtering. So again, I'm going to separate the code into I think 3 or 4 steps. Okay, we'll do it step by step. Then you will get smoothing imaging or edge detected imaging. Okay. So the very first step, again, we need to import. We need to get the local imaging or region in specific region right here, and then we will do the interpolation. So this is actually what we did in the last week, right? So you will need the DICOM read, okay? You will use the get value of a specific range of the matrix. It is the same range that we used in the last week. And you will use the INTRP to do the image interpolation. But right now, I'm going to ask you to use a factor of 4. In the last week, we used 2, right? But right now, I'm going to ask you to use a factor of 4. So for the second input of the interpol function, you are going to put a 4 right there. Okay, so this is the idea that you can do. For the very first thing, you clear and close. So I think this is kind of the habit that you can always do for your script. We use the DICOM read to read the specific DICOM file. Okay, we extract a local region by doing this kind of the get value. We use a specific range of the rows and a specific range for the columns right here. So we get an image on the line local. It is the same thing that we did in the last week. We use the, sorry, we didn't use the interpol. We use the image resize. Okay, we should use the image resize with a second input of 4 because I want you to do this with a factor of 4. Okay, and we can use the image show right here. So again, right now, I'm going to give you a couple minutes. You just try to, I know you have the homework on hand. Okay, just copy what you need, make a new script. Okay, just try to make a new script. Okay. So right now, step number 2, I'm going to show you how to do so-called image smoothing. Let's just take a look about the result, what we are going to get on hand. For the left-hand side right here, this is the original image. You can see the matrix size after the image resize is pretty like the 624 by 684 right here. Okay, you can see the image. However, if you take a look at this region, you may find out this region is not that smooth or not that homogeneous. That means you may see some, dark part, gray part, and for some part, it might be white or bright pixels right here. It's just like continuous changes within this region. I have to say this is caused by noise, by image noise. We don't like this because noise is something irrelevant to our organ or our body or even our tissues. We'd like to suppress it or remove it. So smoothing is kind of a technique and help you to suppress or remove this kind of noise. You can see the results of the smoothed image right here. Compare the left-hand side and right-hand side. You can see now for this area, the fluctuation or the changes become smaller. I won't say there is totally eliminated, but I have to say this kind of a noise is definitely suppressed to a certain level right here. Okay, of course, you may say, teacher, if I get a little bit better right here, I have to say the border of the tooth right here, you can see it become a little bit blurred, right? I have to say that is the effect of the smooth. Smooth means you may have some sharp change. You may have a sharp border. It will become less sharp, I have to say. This is kind of the trade-off, okay? But anyway, smoothing is kind of a technique that we always use in image process to suppress the noise. I think this kind of the idea is pretty famous pretty popular for the brain functional imaging. We always do the smoothing to improve the SNR or signal to noise ratio. Okay, so now you can anticipate after smooth, we will get these kind of things. Everything will become a little bit blurred. And you can think about this, smooth is pretty like average within local region. So every single time when I am looking at a single pixel, what I do is I try to average the value surrounding this pixel. Then I move to the next pixel. Again, I consider the average value within the local area. Okay, that is the idea of the smoothing. Okay. So how to how to do this? I have to say we will use so-called convolution. Convolution, I have to say, it is become very famous nowadays because there is a technique called convolutional neural network. It's kind of a technique for the deep learning. So everyone is talking about convolution. But I come back to the topic that we are talking about right now. What is convolution? Basically, convolution is kind of a technique that we can apply a small matrix or the effect of a small matrix to the target image right here. So let's take a look right here. For example, I have an original image pretty like this one. You can only see black and white. And for the simplest way to represent this kind of the image matrix, 0 is black, 1 is white. Okay, so now you can think, okay, imaging can be represented by this kind of matrix, 0, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0. Okay, so you can see this kind of the shape. If you try to imagine 1 is white, 0 is black, you can see this kind of image, right? But after smoothing, again, I want to say smoothing means that I will try to make any difference less different. Okay, this is very important. So you can see now it's 0 to 1, but on the right-hand side, smoothing imaging will let this kind of the border become like a smoothly changed or slow change for this kind of a border. So right here, this is 0 to 1, but right now you can see it's more like a stair. 0, 2, 3, 5. It's changed gradually. Okay, you don't have the sharp change right here. Okay. So to do this, again, we'd like to introduce the concept of the convolution. Okay, good. Convolution is the idea that we are going to apply so-called kernel right here. Kernel is a small matrix. Normally, this small matrix should much smaller compared to the original size of the imaging. For example, right now, the kernel is more like a 3 by 3 matrix. But the original imaging is more like a 7 by 7 or something. Of course, for the real convolution, you can change the size of the kernel. And the effect of the smoothing would be very different. You can try it later, but not now. And let's take a look. We can use this kind of the kernel. This kernel, you can take a look. It's more like a cross in the center. And this cross comes with the value of 1. But for the corner right here, it's more like 0. So now you can think about this. This kernel will bring the effect more like I will always calculate the average value within this cross area. So once I move the kernel right here, for this pixel, I can calculate the average within this cross area. If I move the kernel to here, for example, I can calculate the average value within here because I always put 1 right here and 0 right here. That means I don't care about the corner area. Okay, so let me give you a real example right here. So now let's try to ignore the white and black. We only care about the numbers right here. Let's do the math. If I'm going to create a smoothed version, what I'm going to do, I will put this kernel, pixel by pixel. For example, I start from this pixel. I will try to overlap this kernel with this pixel. And now you can see the blue numbers right here is the value of the kernel. So I would say it's more like the multiplication. I try to multiply the original value with 1 in this part. And again, I have to say this is a cross area with 1 Okay, and for corner is 0. So basically, I can just ignore the value of the corner, right? Because it will be multiplied by 0. That means nothing. Okay, so I focus right here. So you can take a look right here. For this part, how many 1 did I get? This is 0, this is 0, but this is 1, right? So once I do the multiplication, I will sum it up, will calculate the total number. So right here, I only get 1. So for the new pixel value for this region, this location, you will get 1. Let's move the kernel to this part. That means I'm going to focus on this one. Okay, so again, you look at the close part right here. Now you get 2, 1, right? So 1 by 1, 1 by 1. You make the summation, you will get 2 right here. Okay, then I just move to another part. For example, this part. I'm going to overlay the kernel right here. So you can see the center is right here. Now I'm going to focus on the cross part. Now you get 3, 1, right? So the answer is 3. So you can simply just repeat this kind of calculation from this one. Then you move a pixel to the right hand side, right? You'll get this part. Now you move to here, you get this part. So eventually you can get the full value of the new matrix. Just one by one. We did calculate this one, and this one. But I think you can easily calculate every single one right here. Just follow the rule. So basically, convolution is more like a local calculation. We try to put the effect of kernel. Right here is more like a cross, the average based on the cross area. Okay, not average, sorry, more like the summation of the cross area. I can generate a new value. And this new imaging, based on the kernel design, can bring you different effect. For this example, average is pretty similar like the smoothing. Okay, because you mix everything up. You mix everything up, then you just make the change between these pixels become less and less, right? Because you mix them up. Okay, so what we can do right here, if you want to do this, actually in MATLAB, you can use this very simple function. This is so-called convolve2. 2 means two-dimensional. Again, you can help it, but you can just go for this convolve2. Okay, so what are we going to do? You will input the original imaging. Okay, it can be imaging. It can be, right here, it should be the interpolated, resized imaging, right? Then you can put in the kernel. So kernel is pretty important. You can design your kernel. For the example that we just showed in the last slide, it's more like a 3 by 3 matrix, right? But in this example, I'm going to ask you to use a kernel size like 15 by 15. You can see right here, I use a matrix generator. In the last week, you use zeros, right? It will help you to create a specific size with all the zeros inside. But right now, I'm going to ask you to use ones. So you will create a 15 by 15 matrix with all the 1 inside. So now think about this. In the previous case right here, I only care about the cross, right? Now think about this. If you have the 15 by 15 matrix all with 1, that means if I try to overlay the kernel with our original imaging, I care every single element surrounding this original pixel, right? So I don't ignore the corner. Okay, so this is the concept of the one's matrix right here. So for the second input of the convolve2, you need to put the designed kernel right here. In this example, I named my kernel as the kernel underline SM because this is represented smooth. Okay, I put it right here. But for the final part, please simply put a string. Simply put a string, and it should be written as the same. That means I'm going to maintain the image size. Okay, I'm going to maintain the image size. So if the original image size is more like 7 by 7, the output should also be 7 by 7. If you didn't do this, normally the convolve2 will give you a much larger matrix because, I have to say because we have this kind of situation. The kernel may exceed the original range of the imaging. But I know some of you cannot get this point right now. So just put the same for the third input right here. Okay, so I'm going to give the control back to you. Try to add in these 3 lines after what we did in the step 1. Okay, and just take a look at what you can get in the second figure. Okay, if you did finish, try it. Try to do something different. You can change the value within the line 13. Originally, we use 15 by 15, right? You can change the value. For example, you can change the value to maybe a larger value, like the 50 by 50. 50 by 50. You can just observe what happened, okay? Would the smoothing effect become stronger or lesser? You can check it. Some of you are asking about why we use double. Okay, just take a look. For the line number 5 right here, we did use the DICOM read to get the image matrix, right? But now take a look right here. Image matrix we see in the workspace, it's just saying that it's a 512 by 512 image matrix. It's okay. But you may see something right here. UINT 16. UINT 16 represent unsigned integer. Unsigned means they are always a positive integer. So there is no, for example, -1, -2, no. Unsigned means it should be 0, 1, 2, or something larger than 0, right? And it's always be an integer. So you won't see the floating point like 1.3, 1.2. No, it's always be the integer. So you can just use the variable viewer right here. You can see it's always the positive integer, right? But do remember one thing, when we are doing the convolution, I have to say sometimes we may have floating points. Because sometimes we may do the average, we may do the division. So sometimes we may get the floating points. So basically, convolve2, this function, would ask you to always input the variable with the format of double or single. You may not really know what is single is, but the double and the single are the variable type that can allows you to store the floating point. For this kind of the format unsigned integer, you can never put the floating number in, but it may cause the problem for the convolution. So before you can input a matrix into convolve2 function, you need to use the double. I think it's just one of the choice, but I recommend you to use the double. You can have what does double represent. Okay, it just convert the matrix to double precision. Precision, you can just treat it like a format of the variable. So you can just do a test. For example, I'm doing this right now, double and imaging. So now I'm going to get a new variable named as the image2, but I'm using the double to do the conversion, right? So you will see image2, same matrix size, but now the type is a little bit different. Now it is in double. Just remember, double can allow you or allow MATLAB to put a floating number inside. Okay, always in integer may cause the problem for the calculation or image processing. So this is the reason why I put double right here. So before I input it as the very first input variable, I just use the double right here. Okay, so this is something you need to keep in mind. And I think for midterm computer test, you will use double again. So just to make sure you understand what does this mean, okay? So just continue, okay? So I'm going to ask you, now I believe most of you finished these 3 lines. Please change the value of this part. Now it goes 15 by 15, right? Please try to change the number like the 30 by 30 or 50 by 50. I'm going to do this. For example, I'm going to put, okay, this is the original image. Okay, and this is the original smooth version. So you can compare. This is the original image, right? This is the 15 by 15 smoothed version. But now I'm going to change the value to crazy number, like 50 by 50. It may be too large, but I just want to try it. Okay, if I go for this one, I'm going to do this again. Now, what did you see? What do you see? I have to say crazy smooth, right? It's just blurred everything too much. Now you can see there's no noise right here. I see no noise right here because everything is so smooth. Everything in certain level of the gray. It's perfectly perfect, right? But it's not good enough for the other tissue or organ right here. So I have to say over smoothing can cause the problem because you may also eliminate or remove the important information about the target tissue. Okay, so right here, I would personally recommend you to find a good value or reasonable value to do the smooth. You can just try to switch the number. For example, if I go for the original, the smallest possible size, like the 3, what would happen? Okay, I have to say, giving the other numbers should be optimal. So 50-50 may not be a good value. Go for the other number. So 3 by 3 is a pretty small one, right? Let us just check what is the effect. Okay, you may find out it's pretty similar to the original one, right? Because 3 by 3 is too small. I only consider the pixel next to me. It's not good enough. So for imaging size like the 624 right here, you cannot use too small kernel size. You should find the ideal one. So maybe you can try, for example, 21 by 21. Would it be better? I'm not sure, but you need to try because this is kind of the experiment. But I have to say again, this may be a little bit too blurred. For 21 right here, I think 15 is good enough. So finally, maybe you can try 7 by 7. Okay, it's just kind of the experiment, so just try it. So this is 7 by 7, but I think again it's pretty similar to the original one. So it depends on what is your demand, what do you need, okay? Okay, so I'm going to take the control back. So I think this is the part that you can try to understand what is the effect of the kernel size and what does Convolution do, okay? And again, we can apply this similar idea about the convolution to do very different thing. So now we are going to do the edge detection right here. Again, for the left-hand side, this is the original imaging, original size. For the right-hand side, this is so-called edge imaging. So right here, you can easily see now I just get rid of all of the, detail about this area. What I get right here, the enhanced part or the white curves or white lines right here is the edge of the object. Of course, the object right now is the teeth, right? So you can even see that for each teeth, it has a much more dense outside region and the loose part inside. So you can see actually there are two different edges right here. Okay, so edge detection can help doctors or help the image observer to identify the shape or the border of the object. Okay, so this is the goal of the edge detection. Okay. So right now, again, we are going to use the two-dimensional convolution. But the only change right now, you can see this is the same example, right? 7 by 7 and identical value 0 and 1 right here. But you may find out the edge image would be very different compared to the smoothed imaging. The only difference is this one, the kernel. You can see right now I designed the kernel using O1 for the very first left-hand side column right here. In the middle column, I go for 0. But for the right-hand side, the third column right here, you can see the -1. So now think about this. I'm going to do the same thing. I'm going to overlap my kernel on the original imaging. I'm also doing the same thing, the multiplication pixel by pixel. And finally, I'm also doing the summation within the kernel area, right? So let me just go for the example right here. Again, I'm going to do the calculation. I start from the very first pixel. Now just remember O1 right here, O-1 right here. So basically what I'm doing after multiplication, I use the summation. So basically the idea is more like I'm going to sum up the value in the first column and minus the sum value of the third column. It's pretty similar like this. So it's more like the difference between the left-hand side and the right-hand side. So this is the target pixel. I'm going to calculate the difference for the left-hand side and the right-hand side. So now what I'm going to do, definitely right here, there is empty value, so I can directly ignore this part. But for this example, 0 inside, so I don't need to care about this. I only need to care about right here. So I see 1 right here. Of course, original is 0, so I don't need to care about this. So 1 multiplied by -1, make the summation, it's -1, okay? So let's jump to the next example right here. Now you can see 2, 1 right here. So I get 2. I do the summation, I get 2. And here, simply 0. Even there is 1 right here, but the kernel, the central column is more like 0. So I only get 2 right here. Okay, so let's jump to this one. Now it's a little bit different. You see O1 right here, so you get 2 right here. This is O0. You don't need to care about this. 0, 0, 0. Okay. So now you can see there is -1 right here. For these two are 0. So now it becomes more like the 2 minus 1. So you get 1 right here. So it's more like the difference between the left-hand side and right-hand side. This is so-called the changes, the difference between left and right, right? So you are calculating the difference for each pixel right here. So you can easily do this and to get the imaging. But I have to emphasize this point. When you are using this kind of a kernel, you will get the edge imaging, specifically for the left to right edge. For example, this is a tooth, right? It's more like a circular structure right here. But for this kind of a kernel, again, we only care about the difference between left and right. So you can only see the edge pretty close to the left and right. But for the upper part right here, or lower part right here, you didn't see the edge. Because this calculation only care about the difference between left and right. But if you are using this kind of kernel, 1, 1, 1 and the -1 right here, you are more focusing on the upper and the lower difference, right? So now you may see the enhancement of the upper and the lower edge right here. But for the left-hand side and the right-hand side, you may see the dark signal right here, because now it is trying to calculate for this kind of the actual imaging. You are calculating the anterior and posterior difference right here. So if you really want to get a beautiful circle surrounding these tools, you need to do something like a combination of both left and right and anterior and posterior. So you can see this is step 3 right here. I design a kernel. You can see this is actually for left and right. This is actually for anterior and posterior. Okay, and right now you may see when I am doing the image show, I put an ABS right here. ABS is the function to get the absolute value. Why I do this? Because for the edge detection calculation, you may see some answer. It may be the negative value, because it depends on the part. If you are located in the left edge of the object, you will get the negative value. But if you are locating at the right border of the object, you will get the positive value. I think the idea is pretty simple because you are using 1 right here, -1 right here. If you put oppositely, for example, like the -1 and 1 right here, you will get a positive value right here and negative value right here. It's just a simple calculation, okay? But to be very honest, I don't care about this sign because I only want to know where is the edge. I don't care about whether this is a left side or right side. So what I can do is I can take absolute value. I use ABS function to get rid of this kind of the negative sign, okay? This is a reason why I use the ABS. If you don't use the ABS, I think it would be a little bit weird because your imaging may have the negative value, okay? So basically, go for ABS is pretty important right here. But finally, I have to say we want to get a combined image. I don't want to simply care about left and right and anterior and posterior. I want to get all directions like a circle right here, right? So I do something in this line. I try to use the max function. Max means I'll get the highest value when I compare these two left and right edge and anterior posterior edge. I'll do the comparison and I will get the maximum value. What does that mean? That means for any single pixel right here, I will try to compare the value. For example, this part you can see this is a white, right? But for this part, this is a dark. But because I am using the maximum value function, that means it will preserve the highest one. So overall, for any dark region, if I can get the higher value for another edge imaging, I will get a high value. So this is more like the combination for both direction right here. Okay, so I think this is the chance that you can try to do this. You can try to add these three, and these two codes. Again, you can always find all the codes within the exercise 04.m file. You can do your practice, but I want to give you the instruction of today's homework. So basically, what you are going to do for today's homework, I think I just want you to transform what you did into a function. Okay, into a function. Take a look right here. I need you to create a function. Of course, this function should be named as the prefix letter followed by the student ID. So this is my student ID. So it's pretty similar like the ACE 19, 10, 40, 16 anyway. This is the file name. Also, this is the function name. Do remember, this should be the function name and the file name. Okay, and you should design 3 inputs. It's very important, 3 inputs. The very first one is the original image matrix. So it should be the 512 image matrix by 512 image matrix, okay? But now you can see there is a second and a third input, okay? This second and third input, I want you to give the chance for your users that the user can assign which specific range can be extracted for the subsequent image process. So in the very beginning, we assign, I think right here, we put this in a fixed number, right? But right now, for this function, I don't want these things to be fixed. I want your user can input a specific range that they'd like to extract from the original image. So we're not going to get the value from the 45 to 200 and 170 to 340. No, we're not going to do this. You should allow your user to specify the range. For example, if the user input a range like 1 to 10, then you should get 1 to 10. If the user input the column range like the 100 to 200, then you should extract 100 to 200. So these are the very first things that you should get rid of this certain value. You should rewrite it as the row range and the column range. And the row range and the column range should be specified by your user, okay? So this is the very first things you need to do. This one, okay? And then you will do the image resize by a factor of 4. I think this is identical. You will perform the image smoothing using 15 by 15 kernel size. You will do the edge detection combining both left and right direction and anterior posterior direction, just what we did right here, okay? But finally, you need to output the smoothed version and the edge detected version of the imaging as first and second output variable. Okay, so basically you can modify it directly from the imaging exercise 04.m file within the directory that I provided to you. Okay, so I just want to remind you, do not use the DICOM DICOM read within the function. You should not do that because you should allow your user to input the image array, right? So if I see DICOM read within the function, that is definitely wrong, okay? So no DICOM read within the function. Second thing, do not display any image within the function. So please delete every single image show or figure. Because the idea of this function is simply do the calculation and output two new metrics to you. Okay? So just think about this, discuss it with your teammate. Okay? So you can finish the homework in the classroom. So do it now.